Alright, so from the previous class, we have learned about the absorption of spectrum from the analyte, the concept of AAS. So the detector will detect the loss of some energy in the spectrum due to absorption of the spectrum by the analyte. The process of transferring sample into flame, okay. In AAS, we transform the sample from the first stage is if the sample are solid, we need to digest, and then we need to transform the sample into solution. And then from the liquid state, okay, the sample being pumped into the flame and transformed into a gaseous form, okay, in form of atomized. Okay, the molecule in the analyte will be atomized to the single atom, and then some absorption of energy happen. Okay, from ground state to excited state. Okay, and then the analyte will absorb a certain amount of energy that's similar to the light source. Okay, if the analyte is have similar absorb similar amount of energy from the light source, so it means that some of the energy from light source being absorbed by the analyte, meaning that it is the similar, okay, the atom absorb a similar amount of energy, okay, so that if the light source is for iron, so the analyte might be iron, and then the detector detects some of the spectrum from the iron lamp have been absorbed by the analyte, which is probably iron in the sample, right? This is how the absorption happen. Okay, the atom, okay, when being heated, okay, it will absorb, okay, the light spectrum from the light source, okay, then being inside. Okay, then we have two methods of atomization in AAS. The first one is flame, sample solution aspirated into a flame. The second one is graphite furnace. Okay. Remember, I told you if the analyte is quite volatile, okay, it's quite easily to vaporize. So we need to contain the sample in a closed system. So the previous scientists have invented the graphite furnace, sample solution evaporated and ignite within a closed system. Okay. So this is the color of flame with the presence of the minerals. This is the real AAS. You can saw that the flame, right? We can see the flame here. This is the the sample, and normally we have a distilled water. What is the function of the distilled water at the instrument? It is to clean the tube, the pump, and so on. After we put the sample inside, after we pump the sample inside, we need to pump a distilled water to clean everything, right? History about AAS. Okay, Alan Walsh, father of AAS, who invented AAS in the early of 1954. Look at the diagram, the concept of AAS. Okay, it tells that to eliminate loss of vapor at the thermal expansion, okay, to 3000 Kelvin, example 2/3, it is necessary to introduce sample after preheating of cuvette. But how? This is the idea, because some of the analyte, okay, when transformed into a gas form, from solution to gas form, some analyte in the form of vapor lost, okay, due to the thermal expansion. because we need the analyte to stick to be there, because it will introduced into the flame, but some of the analyte lost due to thermal expansion. Okay, so the need in atomization technique to ensure to complete vaporization of a sample, atomizing and holding it within a limited furnace volume. So graphite furnace was invented. Okay, so both end of the graphite furnace must have a optical window, so that the spectrum that we supply can pass through the graphite furnace, because we need we need the analyte inside the graphite furnace to absorb the spectrum, right? Okay, that is the concept. The sample is placed here. It is not placed by manually by the operator of the instrument, but there is an automatic auto sampler. Okay, there is automatic sampler inside the instrument that will pump the sample with a very small tube inside the graphite furnace. The graphite furnace is not so big. We can hold it with our fingertips. Okay, it's very small. It's about from here to here about I think about 4 cm. It's very small. So the auto sampler will pump the sample inside a droplet of sample. Then the sample will be heated and will be vaporized just inside the tube, so that the it can absorb the light that pass through the graphite furnace. All right. Flame is replaced by an electrically heated in the flame. Remember, our problem is the sample will be the analyte will be lost in the flame for certain analyte. Okay, for example, I gave to you arsenic, what more, arsenic, mercury. We have a special method for mercury. Antimony also will be vaporized easily in the flame. So we are not using flame in the graphite furnace. We just heat it electrothermally. Okay, electrically heated. It will be heated by surrounding. Okay, so a few microliters of sample is placed in the tube that I told you here, and it is dried and shed at lower heats and then vaporized at high temperature. Okay, the atomization efficiency is greater than for a flame, and detection limits are lower, because we have solved the problem, right? The vapor of the analyte just contained inside the graphite furnace, so it is more efficient than atomization using flame. So the atomization using graphite furnace is greater for this kind of analyte, and detection limits are lower. We can detect even at a low concentration. That is meaning of the detection limits are lower. Low detection limit meaning that we can detect the analyte with a small concentration. Okay. Okay, the characteristic of the graphite tube. Okay, suitable tube material and surface characteristics. At high temperature, graphite surfaces are highly permeable to metal atoms. Possible. Facilitates longer residence time and good sensitivity. Dimensions should be such as the whole tube has uniform temperature. Okay, that is the characteristic of the. So the graphite furnace program, the first, okay, when we place, okay, at the first, at the beginning of the process, at the first place, okay, There will be a drying process. It's carried out at time of 10 to 100 seconds and temperature within 50 to 200 degrees Celsius to remove the solvent. And then the pyrolysis step is occur. It carried out at time of 10 to 100 seconds and temperature of 200 to 800 degrees Celsius to decompose. You want to detect analyte. We don't need to detect solvent, the matrix, and so on, right? And then the atomization process happened. It carried out at time of 1 second and temperature of 2000 to 3000 degrees Celsius for atomization of analyte. I don't know what is the sequence, 10 seconds to 1 second, right? But I need to clarify about this. But the times, okay, the time lapse, okay, the times for the graphite furnace program is very, you know, the window of the time, okay, the time frame for the process happen is very small actually. Okay, it's okay when we will meet face to face after this. I will bring all of you to see how the AAS function in the lab. Okay. Now this is the graphite furnace AAS. Previously, okay, I show you the flame right here, but the only thing that we replace in the AAS for a flame and graphite furnace is we have a compartment here. If you are using flame, so we put a flame chamber here. If you want to analyze the sample with the graphite furnace method, so we remove the flame chamber, okay, and then we put a graphite furnace, you know, graphite furnace oven, or we have a graphite furnace, yes, we call it like an oven, and then we put, you know, the auto sampler here, because remember I told you, not the operator who put the sample inside the graphite furnace. We have an auto sampler automatically. The auto sampler have a very small tube that will you know, suck a sample from here, sample compartment. We put a sample, a very small amount of sample, a lot of you know, we can have a you know, a lot of samples could be placed here, but in a small quantity. Okay, for example, we have 100 sample. We can put 100 sample here with only you know, the compartment for the sample, the tube for the sample is about, you know, 10 mil for one sample. So the auto sampler will select, we program it here. So the auto sampler will select the right sample to be placed inside the graphite furnace and being analyzed automatically. Okay, here we can see the auto sampler. We can put the sample tube here. I think more than 100 we can put here. We just program using our computer, so the instrument will run the sample one by one accordingly. And this is the light source that I told you. We have two type of light source. We have H allocated lamp or EDL. Okay. Okay. So this is the AAS. I will bring you here soon. Compare AAS and the graphite furnace AAS. Okay. So look at that. Look at the table. For flame AAS, the liquid sample is only okay. But for graphite furnace AAS, we can sample. Okay. And about the volume of the sample, it is for flame, it is in milliliter scale, but for graphite furnace, we only need a microliter amount of samples. The detection limit for AAS, okay, it can detect within part per million, okay, but for graphite furnace, it can detect as low as part per billion and part per trillion. So it is suitable for trace analysis. Why? Because the sample residence time greater and so will enhance the atomization. So that's why. What is meant by sample residence? It means that the sample in the graphite tube, right? So we have time. So we have time for the detection happen inside the graphite tube. Okay, because the sample not vaporized easily because we contain it in the graphite tube. All right. With AAS also we can detect a multi-element analysis. For flame, we only can detect one element at one time. For example, if we detect lead, so we can only detect lead at one time. But for graphite furnace, we can also detect a multi-element analysis. We can analyze several analytes at one time. For example, lead, cadmium. This is for example, okay, iron. So we can detect both all of three elements at one time. Okay, other than that, we also have, other than flame AAS and graphite furnace AAS, okay, we also have hydride generation AAS, okay, for analysis of arsenic and mercury in water sample. All right, why we don't use flame AAS for mercury, to detect mercury, to analyze mercury? Can anybody tell me why we are not using flame AAS or graphite furnace AAS? Anybody give a suggestion why?
Mercury easily evaporate.
Yes, correct. Because mercury is very easy to evaporate even at low temperature. At 40 degree, it already vaporized. Okay, so we need a technique that not using high temperature for mercury. So there are hydride generation, especially for mercury and arsenic also. Okay, because arsenic is a kind of element that also easily vaporize in the low temperature. Okay. For arsenic, flame will break the arsenic hydride bonding, and for mercury, cold vapor is used to form mercury and hydride. Okay, this is the technique for detection of mercury and arsenic. We are using hydride generation. Okay, we have a comparison for the detection limit, okay, in ppb. For arsenic, in flame, we can detect 150, meaning that for detection limit, meaning that this is we can detect. Okay, so for arsenic, if using flame, we can detect 150 ppb, and if we have a lower than that, so we cannot detect by flame, it can be detected by graphite furnace. Okay, 0.2 ppb. This is okay, ICP radial, ICP exit. This is another instrument. So we can see that this instrument is better for arsenic, right? 3 ppb, better graphite furnace. Okay, and then we have also another instrument. Okay, you can see the table comparison of detection, meaning that if we have if we want to analyze lead, we know in the sample the lead the concentration of the lead. Okay, roughly we know that the concentration is, for example, 20 ppb and above for lead. So what is the method that's suitable for detection of lead in the sample?
GF, Graphite Furnace.
Not so accurate answer, because I told you we already know that roughly in the sample we have 20 ppb and above. So why we use graphite furnace AAS? Because the detection limit is lower. So we need only use flame AAS. Okay, remember it is we in analysis we also consider this thing. What is this? Cost. From your idea, which one is more expensive, using graphite AAS or flame AAS? Which one is more expensive?
AAS-GF.
GF, right?
Right.
Because the graphite, the graphite tube itself only can be used for several times. For example, only can be used for 30 times, and then it need to be thrown away. But the cost for one graphite tube is more than 1,000 ringgit. You get the idea? So this is expensive. So if we know that our sample only have, not only, if we know that our sample have high concentration, okay, for example, I told you, we know the sample have 20 ppb, 20 part per billion and above. So it's only suitable if we use, it's just suitable if we use flame for lead, all right? But if we already know that roughly the concentration is very low in the sample, so then we use the graphite furnace, okay, or other instruments, okay. Okay, in this table, okay, the cost is also increased to the right. Okay, this one is the cheapest one. Flame, we only use acetylene gas to produce a flame, but graphite furnace we need to buy the graphite tube and so on. Okay, and then the other instruments are also expensive. You look at the detection limit. If the instrument can detect at very low detection limit, meaning that it is also expensive for analyzing using that instrument. Understood?
Yes, sir.
All right, this is a cold vapor AAS for for mercury and arsenic I told you, and also some other elements such as selenium. Okay, because it is very easily to vaporize. Okay, so the primary techniques for mercury analysis also could analyze arsenic and selenium and other metal. Well-known technique for detection of arsenic and selenium is hydride generation, whereby the reaction of sodium borohydrate, this is sodium borohydrate and hydrochloric acid, generate by hydride to attach with the analyte in a gas form. So the reaction of sodium borohydrate and hydrochloric acid will generate a hydride, okay, in the form of gas. Okay, so it will be transformed from liquid, okay, liquid with at the low temperature. Okay, at a temperature, because we don't need a high temperature because our sample, our analyte is easily to vaporize. Okay, so at low temperature, the hydride will generate in a gas form together with the analyte. That is what we need. We need to, to transform the sample from liquid to gas. Okay, but if using flame or using graphite furnace, it involve a very high temperature, so it's not suitable for this element. So we use the hydride generation technique. Okay, so now it solves the problem. We can transform the sample to gas at low temperature. All right. What happened to the slide? Some missing diagram in the slide. All right. So it's similar. We have a detector and we have a holocated lamp. Okay. The concept is the reaction between borohydrate and hydrochloric acid. Okay, will produce a gaseous form of sample at low temperature. Okay, and then the volatile will be transferred here together. The hydride with the sample will be here, and the holocated lamp will pass through the tube, and we can detect the absorption. That's why we call hydride generation. This is hydride generation. Okay, and AAS. This is AAS. Okay. Remember, we have several type of AAS. We have flame, so that the atomization is in the form of flame, and we have AAS for the detection. And we have graphite furnace. The atomization is in the form of graphite furnace, and we have AAS for detection. For this, also similar, we have a hydride generation for the atomization, and we have the AAS for detection. Application of flame AAS, we have a lot of application. We have a standard method test for nickel, vanadium, and so on. Okay, in the crude oil. Okay, you are a petroleum engineer, right? So how to detect the metals inside the crude oils? So we use AAS. We use only flame. Okay, to detect nickel, vanadium, iron, sodium in crude oil by residual fuel. Okay, by flame. Okay, and then we have standard test for analysis of nickel alloy by flame. We have a standard method for test the analysis of aluminum in water sample. This application of graphite furnace AAS, we have the standard method, okay, to determine elements, okay, and then we have standard method for detecting the trace element in the water, okay. and we have the standard method of determination of trace element in coal, coke, combustion residues. Okay, from coal. What is coal? In Malay, we call arang batu, right? That is the so we can detect any analyte, okay, in the form of trace elements, as well as the not trace element, not in the form of trace element. Okay, any metal that we can detect using AAS, flame, or graphite furnace, but we need to consider about the analyte first. Okay, what is the analyte? Okay, it is, and then what is the amount of analyte inside the sample? If we know this is at very high concentration and we can only use flame, so we just use flame. Okay, because we need to consider cost in the analysis. If the elements inside our sample is at trace amount, very small amount, so we consider to use graphite furnace. Okay, if we have mercury or arsenic, so we consider to use hydride generation. Okay, there is a lot of consideration that we have before we analyze the sample. So application of cold vapor, we can detect mercury in environmental sample. Okay, for hydride generation, okay, we can detect arsenic and selenium. So in summary, this is the AAS concept. Okay, we have a light source. Okay, and then the sample will be atomized, either use flame, graphite furnace, or cold vapor or hydride generation. And we have our monochromator and detector. Okay, for other instrument, we have this is ICP-MS. So we have a plasma. We transform the analyte, the sample into plasma, and then we have a mass spectrometer detect the analyte. We will learn after this, but for AAS, this is a concept. Okay, we have light source, and to atomize the sample, either we use flame, graphite furnace, or cold vapor or hydride generation. Remember, cold vapor is for mercury and hydride generation is for arsenic and selenium. And then we have a detector. Okay. So do you have any question for this topic? We'll move to next topic next week. Do you have any question?
No, sir.
Okay, understand? You understand everything that I teach you today? Very good.
Doc, I have a question.
Okay, yes, what is your question?
Can you go back the slide before? Yeah. Yeah. No. The next one. Yeah. You said
This
that.
one?
You said
Okay.
light source, right? We are detecting this the light, right, or elements in AAS.
Yes, this is the detector.
Yeah, but here in the light source, are we detecting the light? I mean, are we detecting the light or elements like mercury or
We detecting the light. We detect the light. Okay. In the atomization process, we have either flame, we have graphite furnace, right, or hydride generation or cold vapor. This is for atomization. Okay. When the sample being atomized, okay, it will become single atom, right?
yes?
And then it will become excited. Okay, certain analyte. Okay, for example, the light source. If you use the light source, cadmium light source. Okay, so if there are cadmium inside the sample, okay, so the cadmium will be excited when introduced to the light source with with the spectrum from the light source. Okay, and then our detector will detect a loss of loss of energy from the light source. Okay, so the amount of energy that lost is represented by the will be represented as concentration. Will be transformed. The detector will transform the information to the computer as a concentration. What happens if we don't have cadmium inside the sample? Is there any absorption by the analyte inside the, by the atom that we have been, atomized, by the sample have been atomized? Do we detect any detection if there are no cadmium inside it? No, right? Because the light source is in the form of spectrum that is similar with cadmium. Only can be absorbed by cadmium. If there are no cadmium inside the sample that being atomized, so the detector. So the detector will give the signal to the computer that zero concentration. Understood?
Yeah, that's it. Thank you.
If the sample contained cadmium, when it being atomized, okay, there will be a single atom of cadmium, and the single atom of cadmium will absorb the cadmium spectrum from the light source, and then it will excite, okay, and then the absorption of the energy from the light source will be detected by the detector. So the detector will detect some amount of energy have been lost, and it will transfer the information in the form of, okay, so the signal will be some concentration. For example, 5 ppm, meaning that 5 ppm of cadmium inside the sample. Remember, I told you the instrument don't know about concentration, so we need to calibrate, right? We need to do calibration, right? The instrument only know about the detection, the response. Okay, so what we need to do is, before we analyze the sample, we need to do calibration, a series of calibration. So we need to to prepare a series of concentration. For example, if you want to detect cadmium, we need to prepare for example 1 ppm of cadmium solution, 2, 3 until 5. So then we analyze, we read using the instrument. We have a calibration plot. Okay, calibration plot, the R square should be 0.99. Okay, sorry about the screen. Okay, 0.99. 999 is the best, 0.999 is the best, but 0.997 is also acceptable. So when we calibrate the instrument with the series of calibration solution, so the instrument already know about the concentration. So the instrument will transform the signal in the form of concentration after we calibrate the instrument first. Okay, because before we calibrate the instrument only know about the absorption, right? The amount of energy. But after we teach the instrument, if you absorb this amount of energy, this is 1 ppm. If you absorb this amount of energy, this is 2 ppm. The calibration is a process to teach the instrument. So, and then the instrument memorize the calibration, meaning that the response and the concentration. So after with the analysis, okay, the detection now being transformed in the information of concentration. Okay.
Okay, that's
For all analytical instrument, we need to calibrate the instrument first. We need to prepare a series of standard solution to teach the instrument about the concentration. Okay. Because the instrument, it only can, it only know about, they only know about the response or for example, AAS, the instrument only know about how much is the absorption. But to transform in the information of concentration, we need to calibrate the instrument. Okay, that's it. There are some questions about the test. All right, I'm not decide, right? I will tell you this Sunday what is the topic that will be covered for test. Okay, But don't worry, the test is not so difficult, okay? What I taught you in the class, okay, that will be asked in the test. It's only a simple question. No, don't worry about that. Because you have learned a lot in the class, so that you can watch again the class video, can answer the question. All right, do you have any question? That's all?
No, sir.
Okay, so that, thank you for attending the class. See you next Sunday, okay, this coming Sunday, with a new topic. Okay, right. Assalamualaikum and good morning. Thank you, everyone.
Have a nice
Thank you,
weekend.
Doctor. Bye. Okay, thank you.